Hello, my name is Ariana Angarita,
I'm Faisal Wajdi.
Naguib Shabi.
and this is Group 6A, and we're going to talk about building electromagnetic motor. Magnetic field is a vector field that describes the magnetic influence of electric charges in relative motion and magnetized materials. In most objects, all the atoms inside are balanced. This means that half of their electrons are spin one way and half spin the other way. But this is different for magnets. Inside a magnet, the atoms on one end contain electrons that all spin in one direction, while the atoms on the other end have electrons and spin on the opposite direction. This means that all the electrons line up. This will then create the magnetic field around a magnet. And these magnetic fields can be used in order to make electricity. We will explore this by looking at metals like copper. These have electrons that are easily moved inside their orbits. We will use this to produce electricity.
Our research question is, how does the increased number of magnets in an electric motor system affect the kinetic energy produced by a copper coil wire? We hypothesize that the increment in magnets will result in a greater velocity of spinning of the coil. Therefore, we will observe the kinetic energy produced by the system is increasing.
To set up the experiment, we'll need to first attach the copper strands to blocks of Play-Doh in order to stabilize them. We will then put the magnets directly in the middle of these two copper strands and place the copper coil into the copper strands. And then finally, we will attach the battery to the copper strands using alligator clips. And then we will track velocity of the copper using tracker.
How does the motor work? It is important to remove the insulation from one side of the wire so that the coil is always in contact with the battery through the copper wires. It allows the current to flow through the loop. We leave insulation on half the wire so that the coil, which is the electromagnet, is active only half the time. This allows the magnet coil to push against each other without them pulling each other half of the time, which is what will keep the coil from spinning. Since the loop is in a magnetic field, these moving charges feel forces, as indicated by the pink arrow. Charges moving to the right at the top of the loop feel a push into the screen. Charges moving to the left at the bottom of the loop feel a push out of the screen. These forces work to make the coil turn. When this happens, the insulated portion of the wire will turn as well, blocking the current through the loop, eliminating the turning forces. The loop then goes through full turn, ending up where it began, and the whole thing starts again. Representations of our systems by doing system schemas and free body diagrams. We see here from doing the right-hand rule that we found that the current is parallel to the magnetic field. As indicated, we see that the thumb is the direction of the force, the pointer finger is the magnetic field, and the middle finger is the direction of the current. Before, there will be an upward force on the upside and a downward force as a result of our coil, which will start moving and start spinning in the clockwise direction. We can also see here that the system schema represents the forces that are also included in our system, which can be stop the video and you can observe them closely. It's important to observe that the magnetic force is perpendicular to the plane of the velocity or current of the charge and the magnetic field.
As far as the reason why the coil doesn't spin when there's one or two magnets, it's because it's left on its own, and with only one or two magnets, the coil would never make a full rotation. It would go 180 degrees one way and then 180 degrees another way. Without completing a full rotation, we weren't able to count as data. As far as the rest of the magnets go, since they were able to make full rotation, we were able to count their data, and we're able to plug their values into tracker and find their average position. We took their average position and divided it by the change in time to find the velocity for each number of magnets, and then in order to find the kinetic energy, we simply squared whatever velocity values we got and multiplied it by the mass of the copper coil and divided it by 2.
Based on the data we just collected, it can be said that the increased amount of magnets will also have the increased amount of kinetic energy in the system. In conclusion, our hypothesis was correct. The more magnets will equal the more spins. We also concluded that the more magnets will result in a greater magnetic field. The number of spins is directly related to the strength of the kinetic energy. As we increase the amount of magnets in the system, the kinetic energy also increases. Our sources of error are possibly from the angle the video was taken at and tracker's calculations. We also believe the stripped side of the copper wire may have not been stripped sufficiently. If the copper wire was more stripped, we could have seen more rotation.